Hello guys, welcome back to Maison African Motives, still on Electrotechnics N4, that is working on the principles of electricity from the question paper of April 2020. We are going to have a revision, knowing how do they ask these questions, how are we supposed to answer such typical questions. So we've got the first part of our question, which is 2.1, where we're given what does the term electromotive force mean? We are given the definition. What does the term mean? That is a definition for that term. All right, that is 2 marks for that. So if we are to check here for the electromotive force, we are talking about the force which actually tends, that is that force which tends to produce an electric current in a circuit. So that is what we are referring to as the electromotive force in this case. All right, so that was the first part of our question. Then the second part, we are given 2.2, what are the 5 characteristics of magnetism? As long as you're dealing with magnetism, what is it that we consider? These are the characteristics. What is it that you know about these lines of flux, everything about magnetism? All right, so let us get into consideration. So the first thing, the lines of magnetic flux never intersect. So you're saying the lines of the magnetic flux, they will never intersect to each other. Then each line of magnetic flux forms a closed loop. The lines of a magnetic flux are like stretched elastic cords, always trying to shorten themselves. Lines of magnetic flux which are parallel and going in the same direction repel on one another, or that is there's a repelling that is happening between the two. Then the direction of a line of magnetic flux at any point in a non-magnetic medium such as air is that of north-seeking pole of a compass needle placed at that point. So you're saying whenever you're given a direction that is of a line of magnetic, but it's a non-magnetic, then we are given examples such as air, we've got paper, we've got air, these are non-magnetic. So it is always going to be a north-seeking in the North Pole, just like a compass in the needle placed at that point. So this is what you're having. So these ones for our theory, guys, I just encourage you to revise your theory as much as you can so that you, yes, understand as much as you can. All right, so let us quickly rush to the calculations. We've got 13 marks for question 2.3 and question 2.4, which needs us to apply the calculations. All right, we are given in this case 2 series circuit branches of 6 ohms and 4 ohms. So there are 2 series circuit in this case. The first one has got 6 ohms and 4 ohms. All right. And the other one has got 10 ohms and 5 ohms respectively. So meaning to say we have got these 2 in series. They are connected in parallel. So take note, these 2 in series and these 2 in they are connected in parallel. So we've got something of this nature from what they are trying to say. We've got 2 resistors in this case. This is what we have. The first one is a resistor of 6 ohms in series with a resistor of 4 ohms. All right, so we've got 2 resistors in series here. That is our 6 ohms. And the 4 ohms in this case, we can just refer to as R1 and R2. These resistors, they are connected in parallel to these 2 resistors again in series, the 10 ohm and the 4 ohm. So we have got the 10 ohm in this case and the 4 ohm in series. So this is what we have, the 10 ohm here and the 5 ohm. So this is the 10 ohm and the 5 ohm in series. All right, so this is like something like this that you are given. So we are told that these combinations that you are given like this, they are in series and connected in parallel. The series part is then connected in parallel to a battery now. All right, so let us just have this. We can just say this is our R3. All right, so we can just say this is our R3, which is 10 ohms. So that is our 10 ohms. This is R4, which is 5 ohms in this case. All right, so this combination that we see is connected like this. So we're going to just have to the voltage source. All right, so let us take this whole combination to our voltage source. All right, so this is what is happening. So to our voltage source here, we are going to have a voltage source that has got an internal resistance. We are saying this voltage source has got an internal let me just indicate it, but the internal resistance, we cannot even show it, but let's just say we just indicate it like this so that we know that there is an internal resistance here of 0.25. So that's 0.25 ohms. The voltage, the EMF of the voltage of the battery in this case is 25 volts. All right, so just this is a sketch, okay, just a sketch of something that what it looks like. So the question was to calculate the potential difference across each external resistance, not internal. This is our internal resistance. The external resistance is now we are referring to this one, R1, R2, R3, R4. So meaning to say we need to calculate VR1, we need to calculate VR2, we need to calculate VR3, we need to calculate VR4. But how is this possible? All right, let us take back to our normal circuit, guys, and understand what is happening here. We know that if we can obtain the current which is flowing towards here, this current is going to branch into this branch here, also into this branch. So let us say this is our total current. Then this we can name it as I1, this we can name it as I2. So meaning to say, if we can calculate these currents, it's easier for us to calculate the voltages, because here we are going to have a current and a resistance. Remember, where there's current and resistance, we can calculate voltage, because here we simply need I1 times R1. The same thing here, we are going to need I1 times R2. On VR3, we are now focusing on I2, meaning to say we are going to need I2 times R3. To calculate VR4, we are going to need I2 times R4, because they are having the same current of I2, these two resistors, which are in series. So you're going to have I2 times R4. So as you can see, what is missing here are the currents I1 and I2. Once you can have these currents, therefore we can calculate these voltages. All right, so how can we calculate the currents? The first thing, let us focus on the resistance first. If we can have the total resistance, then it will be easier for us to have the total current. All right, so meaning to say these two resistors in series, we can add them. Remember, in series, we can add 6 plus 4, which is 10. So we are going to have our circuit like this. Let me just shorten this so that you can understand me. As a single resistor here. Also here, we are going to have this as a single resistor. Because they are in series, so we can just connect them direct like this. So this is what you're going to have at the end. Our internal resistance here connected like this. All right, so what I'm trying to say is we have got R1 and R2, these ones which are in series. So we add 6 plus 4, which is going to give us 10 ohms. So we are going to have 10 ohms here. 10 plus 5, which is in series, this one is going to give us 15 ohms. So if you understand properly, you're going to see this current that is flowing here. This is the current that is flowing on I2, this one. And this is our total current that we are supposed to calculate here. This is your total current. And this is your E, which is 25 volts. The internal resistance, don't forget, it was 0.25 ohms. So this can help us. From this circuit, we can understand much better that it's easier for us to have the total resistance, because the total resistance here is going to be these two in parallel. Remember, we've already added them. They are now just a single resistor. So you're going to have the product over the sum of these two resistors in parallel. So you're going to have RP plus the internal resistance. So meaning to say our RT is going to, remember, in parallel, we are going to use the product over sum. There are two resistors, so we can simply use product over sum. That is the product of the resistors, 10 times 15 over the sum, 10 plus 15, plus the internal resistance of 0.25. All right, so this will give us the total resistance. The first part, if we are to simplify, this is going to give us 6 plus 0.25. So 6 plus 0.25 is going to give us 6.25 ohms. So we have got the total resistance. That means we can be able to calculate the total current in this case from the total voltage, which is our EMF, over the total resistance. So that means our total current is going to be 25 over the total resistance of 6,25. All right, that means our total current, in this case, if we are to divide properly, we are going to obtain 4 amps. All right. Remember, our focus is to calculate I1 and I2. These are the currents which are missing to calculate the voltage, like I said, I1 and I2. So how can we calculate I1? From this diagram, we can properly see that, okay, this is where we are having our current I1 in this case. I mean, the total current here of 4 amps. And this current is going to branch into this branch here and also into this branch. So meaning to say we can apply the current divider rule to calculate current I1 and to calculate current I2. Remember, from our current divider rule, just like on our Norton's equivalent circuit there, where we talk about calculating using the current divider rule. So using our current divider rule, so we are going to apply current divider rule in this case, which says that to calculate I1, you use the opposite resistor on top. This is I1. So you use this opposite resistor on top. So it is going to be 15 on top. So that is 15 over the sum of the resistors, the ones that are sharing the current that you're supposed to share. So these are the two resistors, the 10 and the 15. Remember, we combined them before. So you're going to add 10 plus 15 times the current that you are sharing. This is the current that you are sharing, which is the current of 4 amps. So that means we can calculate I1 from this. So I1 is going to give us 2,4 amps. So we can have this, which is 2,4 amps, which is the same thing. In order for you to calculate I2, you can use the same thing, or you can use Kirchhoff's laws, since we have got current flowing towards the junction. So you can say I2 is equal to I minus I1, that is total current minus I1, or you can simply use again the current divider rule. This time we are calculating the current across the 15 ohm resistor. So you use the opposite resistor on top. So that means we are going to have 10 this time on top. So that is 10 over the sum of the resistors. You add the resistors 10 and 15. So that will be 10 plus 15 times the total current that you are sharing, which is the 4 amps in this case. So multiply to the 4 amps, we are going to obtain I2. So that means I2 is going to give us something like 1.6 amps. So as you can see, if you add these two here, if you add I2, which is 1.6, and you add I1, which is 2.6, they must give us 4 amps, which is our total current. But this is not about our question. Our question is to calculate, take note guys, our question, it is limiting us to calculate the potential difference across each of the external resistance. So that is why we need to calculate I1, because we've got this part here. So we have calculated I1. We said I1 here, it's 2,4 and I2 1,6. So this is what we have. I1, we can have it on our diagram. We said I1 is 2,4 amps. So we've got 2,4 amps. I2, which is 1,6 amps. So if you take from the original diagram now, we can see that this is the current, the current of 2,4 amps is flowing towards this resistor, also is the same across this resistor since they are in series. So that means we can calculate their voltages in this case, like I said, from these formulas. So that means we can have our VR1 in this case, which is going to be, we said I1 times R1. So I1, which is 2,4. So you're going to have 2,4 times R1, which is 6. So if you multiply 2,4 times 6, we are going to obtain 14,4 volts in this case. All right, we move on to VR2. So VR2 is I1 times R2. I1 is still 2,4. So that's 2,4 times R2, which is 4 ohms in this case. So if you multiply 2,4 times 4, you're going to obtain 9,6 volts. All right, the same thing on VR3, we are going to have I2 times R3. This is our VR3 here. So it is going to focus with I2. So that's I2, which is 1,6 amps times R3 in this case, R3, which is 10 ohms. So if you multiply, this will be 16 volts. All right, the same thing on our VR4. This time we are talking about I2, the same current flowing because it's a series circuit. So it is 1,6. So that will be 1,6 times our R4 in this case, which is 5. So 1,6 times 5, this will give us 8 volts. All right, so these are the voltages that we are being asked to calculate from our question. The external voltages, that is VR1, VR2, VR3, VR4, according to the way that you have labeled your diagram. Maybe this is your R1. So it depends with how you have labeled your diagram, but as long they correspond to these voltages that we have calculated now, this is what you can do or how you can play around with this typical question. All right, let us check the other part of our question. That is having 3 marks, which is 2.4. So on 2.4, we are given the resistance of a coil of wire increases. All right, so this is what we have. All right, so let me try to increase so that you can see at this like this. All right, so this is having 3 marks. This is our question that we are given, which is 2.4. Let us try to take down our information, which is the data that we are given. So we have got the resistance of a coil of wire increases from, take note, from, that is our initial starting point. So it was at 40 ohms. So that is our initial, which is R1, which is at 40 ohms. That is the temperature at that point. So we are given also the temperature when at the first point. So we have got T1, which is 10 degrees Celsius. 2, that is from 2, that is 2, that is now the second one, that is our T2 or our R2, whatever, but from, that is the initial, your starting point, or your starting point in this case, or the starting point from where it is given from, that is where you are starting. So that's your R1, your T1. That is where we are having the second points now, which is our R2 and R3 and T2 in this case. All right, so that is what we can have. So in this case, 2, the resistance R2, which is 48,25 ohms at this temperature. So it corresponds to this temperature T2 of 60 degrees Celsius. So these two, they go hand in hand. Also, these two here, they go hand in hand. That is what we need to understand. All right. So the question is, find the temperature coefficient of the conductor at 0 degrees Celsius. So we need the temperature coefficient at 0 degrees Celsius. So how are we going to have this? Remember, whenever you have got different resistances and different temperatures, but referred to at a temperature coefficient of 0 degrees Celsius, we are going to use the formula which are also given in our formula sheet, which is R1 over R2 is given as, which is equal to 1 plus the temperature coefficient is 0 degrees Celsius times T1 over 1 plus the temperature coefficient is 0 degrees Celsius or times T2. So this is the formula that we need. So since we are to calculate the temperature coefficient in this case, let us make it the subject of the formula. Let us play around with our calculations and make our temperature coefficient at 0 degrees Celsius the subject of the formula. So how can we do so? We can cross multiply. So this means R1 is going to multiply everything in this bracket. R1 times everything, 1 plus alpha, the T2 like this. R2 is going to multiply everything. That's R2 times 1 plus the temperature coefficient times T1 in this case. All right. Expand by resistor R1. That's R1 times 1. We're going to have R1 plus R1. Everything remains as it is here. R1 times 1. R2 times 1. This is R2 plus R2 multiplies this part. So it's going to be R2 alpha naught T1. Remember, what we need in this case is to make our temperature coefficient of resistance, this one out at 0 degrees Celsius, the subject. So we are going to take this to one side of the equation. It's either you're going to transpose this side or you are going to transpose it this side, depending with what you want. Okay, so in this case, I'm just going to take these ones to this side. That means I'm going to have R1 alpha naught T2 minus R2 alpha naught T1 is equal to, then I will transpose R1 to this side. So it's going to be R2 minus R1. All right, so we are going to have on this side as R2 minus R1. Remember, what we need is to make this the subject. And from our mathematics, you know that if a term is on different terms, the one that you want to make the subject, we are going to factor it out or to factorize that term. So if we factor out this alpha naught, we are going to remain with R1 T2 minus R2 T1 in this case, which is equal to R2 minus R1. So we can divide by the bracket since this is under a multiplication. So we can divide by the brackets, both sides. The moment we divide by R1 T2 minus R2 T1, both sides, we are going to remain with alpha naught as the subject in this case. So this here will cancel. So this will cancel. So meaning to say we've got our temperature coefficient here, which is going to remain as, so our formula is going to be equal to R2 minus R1, everything over R1 T2 minus R2 T1. So in our electrotechnics, change of subject is the basic thing that we need. Sometimes they might just give you information. They will just ask you, make this one the subject. So it is the core part of our syllabus from our mathematics N3 there, change of subject. So let us try to work on much questions as we can. So what we need now, we are going to substitute our values, R1, T1, R2, and T2. These are the values that we have. So in place of R1, we are going to substitute 40. In place of R2, we substitute 48,25. In place of T1, 10 degrees. In place of T2, 60 degrees Celsius. All right, so this is what you're going to do in this case. So let us substitute our values here. So if you are to take note, we are going to have our alpha naught as R2. Remember, R2 was 48,25 minus R1, which was 40 ohms, everything over R1, which is 40 times T2. Remember, T2 was 60 degrees Celsius. So this is 60 multiplied together minus R2, which was 48,25 times T1, the temperature one, was 10 degrees Celsius. So this is going to give us something like 0.00430 that's 30247 and so on and so on and so on, depending with what you're going to have. But this is given as per degree Celsius. Remember, that will be given as per degree Celsius. So we can round off to 3 decimal places, which is going to give us 0.004. Right, yeah, that's 0.004 per degree Celsius. That is what you have. But as long you have written your values, the first thing is what you need is to at least try to write as many values as possible before you round off your final answer. All right, so that the examiner will know exactly what you had before from your previous calculations that you have to give the answer. So these are the steps that you might have. Yes, you can substitute your information direct on the formula, yeah, and calculate your temperature coefficient of the temperature coefficient of, in this case, direct as it is, which is fine. But making the part that you need to calculate the subject is the best. Once you make it the subject, then all you need is to substitute the information that you are given, because you have what you want to calculate as the subject. So you can simply substitute your information, then from your calculator, you can simplify. That's it. Okay, guys, that's what we had from this question paper, having a total of 20 marks from April 2020 exams. So let us try to work as much questions as we can. But for now, that's it, guys. From Zone African Motives, till we meet again.